Hello everyone and welcome to another video. Today I wanted to have a quick discussion on the 4-quadrant inverse tangent. So since we're talking about trigonometry, I think this is the typical picture you see with almost every trig diagram to help us remember what are the definitions of sine, cosine, tangent, all that kind of good stuff. And I think you'll remember, right, that the idea with tangent is that tangent is just basically measuring the ratio of y over x for a given angle theta, right? So tangent of theta is nothing more than y over x. Right? So it's really darn simple, right? So we can actually plot this function, the tangent function, very, very easily, right? If we look at theta, and I want to now plot it against tangent of theta, right? This again is just this ratio of y over x. So let's see, when theta is 0 here, right? The ratio is y is 0 and x is non-zero, so this starts here at 0, right? And then when theta is 90 degrees or pi over 2, right? Y is something non-zero and x is 0. So this thing is going to blow up to positive infinity around here, right? This here is exactly pi over 2, right? And then similarly, if theta was negative, like pi over 2, we'd have the exact same other issue, right? Y would be a negative non-zero value, x would be 0, so this would blow up to negative infinity over here at negative pi over 2. So this thing kind of looks like blowing up this direction and then blowing something like that. And then it just kind of actually repeats, right? If you, again, think about this long enough, we would basically get behavior like this and something like that, right? So that's what the normal tangent function looks like, right? Now, by looking at this plot, what's interesting about this is we realize here that tangent is not a one-to-one function, in the sense that for any input theta, right? Yes, there is a output, but it's not a single output, but that's not the same in the other direction. Meaning, if I wanted to pick a given y over x value, right? Like, I don't know, like this value here, right? If you look at this and you follow this along, right? There are multiple possible solutions. Here's one, here's one, here's one, right? And this thing repeats. In fact, there's an infinite number here. If I wanted to go look up what is the theta that corresponds to a specific y over x, or in other words, what is the x value that corresponds to a specific y value, right? There's multiple values that it could return. So what ends up happening, right, is that for any given value of y over x, right, we actually have to pick which value of theta do we want to return when someone says, okay, give me what is the theta that corresponded to a specific y over x, right? So most software implementations will choose a range in this region. So let me maybe do this in another color, blue. So most software packages will go ahead and return something in this range. So let's just write this down. So let's just say most software returns values in this range. So in other words, if we wanted to plot the inverse tangent function, so let's do that. So let's just go ahead and plot this sort of in the other direction. So in here we have theta on the y-axis, and then over here we have the ratio of y over x on that axis. And now I want to basically plot arctangent, or sometimes referred to as the inverse tangent function, right? What you'll end up with is you'll only look at this section. So we'll turn this on its side. So what this is going to look like, right, is you'll have this here at pi over 2 and then minus pi over 2, right? And then for any value of y over x, this thing, I mean, it's going to look like this. Something like that, right? It only carved out this single chunk here. So what the issue with that is if you think about it long enough, what this arctangent or this inverse tangent function does is, again, you pass in any value of y over x, and it's only going to give you a value of theta ranging between negative 90 degrees and positive 90 degrees. So really, Coming over here, and again, let's keep it in blue to denote this, all the arctangent function is going to do, it's only going to return theta values in sort of this top quadrant and this bottom quadrant down here that I'm kind of coloring in blue, right? So let's just quickly note that here. So what's interesting is that this arctangent, or the inverse tangent, whatever you want to call it, that function that looks up just this section, only returns values in these quadrants, right? And this can cause a problem because in some situations you might get quote-unquote incorrect results. So for example, give me a second, let me erase some of the board and let's look at an example where this can go pear-shaped. Okay, so let's look at an example. Let's say, how about I've got an aircraft or something like that. I've got an airplane, I'm going to draw it like such. Okay, and let's just consider it's moving around in the plane, and maybe we'll attach a coordinate system to this. Here's X and here's Y. Let's say that this plane is flying along and it's got some velocity vector. I guess I'll do it in green like I did over here. So the velocity vector looks something like this, right? And I don't know, for giggles, let's make something up. Let's say that it's got a X component of velocity of say 10 meters per second and a Y component of velocity of say 4 meters per second. Okay, and now what I want to understand is I want to understand what's the angle that this velocity vector makes with the horizontal, or I don't know, the east direction, however you want to think about this, right? Okay, so how are we going to do this? Well, what you're going to probably do is you're going to run over to your concept of tangent, right? So tangent of theta is just y over x, right? So therefore, the thing theta that I'm interested in, right, isn't this just tan inverse of y over x? Okay, so what's the y value in this case? It's 4, so this is same thing as tan inverse of 4 over 10, right? So this is tan inverse of, I don't know, 0.4. Right? Okay, so far, no problem. What you're going to then do is you're going to come over here to the inverse tangent function, right? And you're going to go look up where's this value of 0.4. Shoot, I should have drawn something. Like, let's make it up here. It's 0.4. It's right here. Okay, so I'm just going to go look up, find this value, come over here, and I think, oh shucks, I didn't do this in, I think I did this in degrees. This is like 21.8 degrees. I apologize, this is in degrees, this is in radians. You guys get the idea. In fact, tell you what, instead of me doing this, let me flash up a screenshot of when I type this into MATLAB or Mathematica and ask it to do this. Using in MATLAB, I can just use the atan function. So this is MATLAB. And then in Mathematica, I'm going to use the arctan function, or you run over to your calculator and you plug in inverse tangent, however you want to do this, right? This is a trivial calculation, right? And what this thing spits out, again, here's a screenshot of what it did for me when I plugged it in, but you basically get theta is, in degrees, it's 21.8 degrees, right? Okay? And that seems totally fine, hunky-dory, and that seems reasonable, right? This looks like 21.8 degrees. Right? Okay, now why don't we change this slightly? So what happens if, let me erase this section on the board. Let's look at a second scenario and see what might happen. So again, let's draw the aircraft, but now I'm actually going to draw it in the other direction. Let's say that we've got X, Y, and now the aircraft is pointing this direction. So here's the tail, here's the wings. Oops, sorry, I didn't draw this very accurately. Something like this, right? So now the aircraft is going this direction, right? And let's give it the exact same components of velocity. Okay, so in this case, this is now X here. Again, this is 10 meters per second. This is 4 meters per second. And again, I'm interested in now, I guess, this entire angle, right? This is the angle theta. I want to know how far is it from the X value, right? So the issue now is we would do the same thing, right? You would say, okay, this angle theta is tan inverse of y over x. Okay, so what are the x and y in this case? So in this case, x is actually what? It's negative 10 meters per second, right? Because it's in the opposite direction of this x. Y here is minus 4 meters per second. Exactly, same thing, right? It's in the other direction. Okay, so you plug this in and you can kind of see where this is going wrong, okay? So y is negative 4 over x, which is negative 10, right? Now here's where we have an issue, right? The negative signs kind of cancel out, right? So you get 4 over 10, right? Which is now tan inverse of 0.4. So this is the exact same thing we did earlier. So by the time you pass it to this tan inverse function, it's going to look up the exact same location and spit out the exact same result, right? So this is going to give you 21.8 degrees, which is clearly wrong, right? Because really, we see that it should be actually what? It should be 180 degrees plus 21.8, right? Or I guess the equivalent of the negative value going in the other direction. Long story short, this is the wrong answer, right? Now, and you can kind of see where this went wrong, right? The reason it went wrong is because we only passed a single input argument to the inverse tangent function, and this information about which quadrant it was located in, right, that was kind of encapsulated and embedded in these negative signs. Well, that got lost here before we were able to pass it to the function, right? So the function has no idea which quadrant are you in when it's trying to make this computation. So this is why if you just use the normal atan or the arctan function in Mathematica, this is kind of let's put an X in here, or maybe we should put like a warning sign, right? You got to be a little bit careful here because you might lose that information about which quadrant you want to be in. Right? So that's exactly why this shortcoming is why we now have the atan2 function. So what do we have, right? We saw that the atan function by itself, the version of atan which basically takes in a single input argument, that was bad or insufficient, right? So now a lot of software packages will implement the atan2 function, which actually takes in 2 separate input arguments. So you give it the y component and then the x component, okay? And what atan2 is, this is basically implementing what's known as the 4-quadrant inverse tangent. So what this thing implements is, it actually is almost like kind of a heuristic statement here, where what this basically will return is, it will do your normal atan of y over x, right, if x is greater than 0, right? Because we saw in the case of x is greater than 0, right? Again, if we draw the circle that I had earlier that I unfortunately just erased, right? We saw that the normal atan function, it returns values in this quadrant, and it does that correctly, right? So again, here's x and y. So we see when x is positive, yeah, the normal atan function works great. The only time this thing starts messing up is if you want results that are in some of these other quadrants here, right? So it does this if x is does 0. It does, whoops, I guess sorry, I was doing this in green. Got too excited and used the wrong color, so let's just keep going with this. So atan of y over x plus pi, right? We saw we had to add on pi, right? And this is if x is less than 0 and y is greater than or equal to 0, okay? It will then return atan of y over x minus pi if x is less than 0 and y is less than 0, right? So that covers, these other two are basically these other two quadrants here, right? So it'll get you the correct result. And then finally we have some of these edge cases where this will return exactly 90 degrees if x is 0 and y is greater than 0, right? So that's one of these edge cases. It will return minus pi over 2 if x is equal to 0 and y is less than 0. And this thing is actually undefined, right? If both x and y are both exactly 0, right? So long story short, this is what's known as the atan2 function, or the 4-quadrant inverse tangent. So again, this is sort of the MATLAB name for it. So MATLAB implements this as atan2. Mathematica implements this as, again, it's called arctan, but you pass it in the x and the y, okay, components. And again, maybe here's a great spot to maybe also put a big giant warning sign. I don't know if I should have done this in red. Maybe I'll highlight this in red. But you have to be very careful when you are dealing with different software implementations of this, or actually of any function, right? So MATLAB decides to ask, again, both of these things take in two separate input arguments, okay? The thing though is MATLAB, they expect the first input argument to be the y component here, and expects the second input argument to be the x component, right? This component. Mathematica, just to be different, wants it in the exact opposite order. It expects the first input argument to be x and the second input argument to be y, okay? So you just got to be a little bit careful when you do this, okay? And so just, again, read the manual, right? RTFM, when you're looking at different software packages and making sure you understand how to call them appropriately, again. Okay, so now, again, so here's a screenshot. When I go ahead and plug this into MATLAB or Mathematica, and I basically go, I guess, and let's do this for the sake of completeness, in MATLAB, if I say atan2 of, let's use our exact example we had over there with the aircraft, right? Now this is -10 and oh no, sorry, I did it exactly in the wrong order. I want the y component first, right? -4 and -10, right? This thing will now spit out, basically, you get -158.2 degrees. And then if you do this in Mathematica and you go arctan of 10 and 4, -10 and -4, right? You get the exact same answer, 158.2 degrees. Right? So here's a screenshot of that, again, dealing with degrees versus radians. I'll let you figure that out. So, yeah, so this basically solves our problem. And if you think about this, this phenomena is not actually just unique to just tangent, right? You could extend this to other trig functions like sine and cosine. Maybe let's talk about that real quick. All right, so here's our same picture, and we could consider now, how about the function, how about cosine of theta, right? Which we know is just the ratio of the x component over the hypotenuse. So again, if we wanted to plot theta versus cosine theta, I think, again, any middle schooler will tell you this looks like something, +1 to -1, right? It starts here, and then at pi, we end up down here, so it's basically something like this, right? In both directions forever, right? So again, we see the same thing. Cosine is not a one-to-one function, right? So its inverse, if we wanted to pick an inverse value, like say here, there are multiple values of theta. In fact, again, an infinite number of values of theta which correspond to that same y value, right? So again, we have to pick a range of values, or most software packages, when you want to go ahead and plot the inverse of this guy, right? When you want to plot theta on the y-axis and then the ratio x over h on the x-axis, you gotta have to pick some kind of range. So the ratio x over h, right, this was cosine of theta, okay, and we know this runs between -1 and +1. So again, what we're looking for is the inverse values between -1 and +1. So most software packages, again, are gonna have to pick a specific range of values to return. So they're gonna return these values here, right? In this section. So really what this inverse function is going to look like, if you plot this out on most software platforms, it's going to look like it's going to return a value between 0 and pi, right? So here at -1, this is going to give you a value of pi, right? And then at +1, this will be 0, like such. So to basically go, something like that, right? So, and again, what we see here is a cosine returns values in the range of 0 to pi, right? Or 0 to 180 degrees, however you want to think about it, right? So in effect, again, this tells sort of half the story, because it will only return values of theta which correspond to sort of these top two quadrants that we're shading in blue up here. right? So again, this could be a problem depending on your application. It really doesn't show up too often, but you know, say you wanted a value of theta which corresponded to a picture like down here, right? So here I'm looking for a negative theta value, or something that corresponds to down here in these bottom quadrants. So again, you might be tempted to do a very similar thing. We'd almost want to implement, instead of a cosine function, we almost want an a cosine 2 function or something like that, right? So now, I guess this is where it gets a little interesting. The hypotenuse is typically, usually, I mean, it's always positive, right? So it might be hard to pass in like an x and an h, because this h is, it's going to be hard to determine, you know, do you mean a -1 for a hypotenuse means that you're actually looking for something in the bottom 2 quadrants as the returned value. So instead, maybe, you know, another way you could do this is, you know, you could still continue to pass into this a cosine 2 function. You could pass it the ratio of x over h, but then you'd almost give it like another flag here with like like, I don't know, how about quadrant? Just give it a flag here. And basically what you could implement here is, you know, you could again do the normal a cosine of x over h, right? If this quadrant flag, you know, equals, I don't know, make something up, like quote unquote top quadrants, right? And then you could do like negative a cosine of x over h if quadrant equals, you know, bottom quadrants. Right, so just another alternative implementation here. So again, this does not show up very often. You definitely see situations where you need the 4-quadrant inverse tangent coming up a lot. But again, there's nothing special about it. Really, we're just talking about a way to make a ambiguous inverse of a non-one-to-one function, make it a little bit more clearly defined here, right? That's really all that we're talking about doing with this inverse quadrant, or with the inverse. The 4-quadrant inverse tangent. So, all right. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you scroll down a little ways and just click on that subscribe button, it really does help me continue making these videos. We're going to have a lot more videos discussing, we're actually going to build off of this and use it to actually set the stage for complex numbers, which then sets the stage for ordinary differential equations down the road. So I hope I'll be able to catch you at one of these future videos. And remember, the new videos come out every Monday, so I do hope we'll be able to chat again at one of those, and we'll all learn something new together. So with that being said, until I catch you at a future discussion, I think I'll sign off for now. Thanks. Talk to you later. Bye.